Good afternoon. Okay. Good afternoon, everyone. Welcome to streamparse, real-time streams with Python and Apache Storm with our speaker, Andrew Montalenti. I will pass it over to you.
Hey, everyone. So yeah, before I actually get started, I'm just going to give a quick background on me. I'm the CTO and co-founder of Parsley, which is a real-time web analytics company. I've been hacking on Python for over a decade. I think this is my 4th or 5th PyCon. And Parsley runs a fully distributed team, just in case there are people here looking for remote jobs in the audience. You can follow me on Twitter. Another nice thing I did is I actually scheduled some tweets to go out from my account during the talk, which have links to the slides and all the materials related to it. So you can find those online too. And so the title that I changed this talk to was actually How to Defeat the GIL with Apache Storm. And how many people in the audience here went to Dave Beasley's coroutines talk or concurrency talk? Yeah, so almost all of you, which is great. It was actually I didn't know he was giving that talk. I watch a lot of Dave Beasley's stuff, and it was a great talk because it showed that in all of these different concurrency models in Python, the GIL tends to get in the way of true concurrent processing. And this diagram is actually from another Beasley talk where he discusses the contention that goes on multi-core and single-core machines with both with multi-threading models, right? And so what do most people do when they run into GIL problems? They tend to set up queue and worker systems, right? Even Beasley said that this was a common way that people solve this problem. How many people here have built a large queue and worker system before? How many people here really love the queue and worker system they built? Yeah, almost no one, right? So queues and workers tend to get pretty gnarly operationally. Whether you're using 0MQ or Redis or RabbitMQ, and whether you're using cron jobs or RQ or Celery, it tends to be that when you start going in the direction of queues and workers, you start drawing diagrams that look like this, which is a diagram I drew of our queue and worker system at Parsley when we got to a certain scale in 2012. And basically, it starts to look like this operationally, right? Where you're like monitoring a million dashboards in order to get an understanding of what's going on. And so one thing you might say, like Raymond Hedinger does, is there must be a better way, right? And I think there is a better way, and it comes with a piece of infrastructure called Apache Storm. So when we first discovered Storm, we read that Storm was a distributed real-time computation system, and it basically simplifies worker and queue systems. And we thought that was great, but we wondered, what about Python support? Because Storm is actually written in Java and a mixture of Clojure as well. Well, that's actually exactly what streamparse is about. So that's what you'll learn about today. So just to give a little background on Parsley, we work with these big media companies that run high traffic websites, like some of the logos on the screen here. And we build real-time analytics dashboards for those companies. And we also build APIs like ones you might find on websites like thenewyorker.com that make live content recommendations to users. So we're dealing with billions of page views and millions of visitors every day. And basically, when I describe this problem to most people, I hear responses like this. Python can't work on this problem. It's a toy language. It can't scale. You really should have used Scala or something like that. And I hate hearing this because basically for 10 years, I've heard about how Python can't scale, and yet I've continued to ship system after system that scales with Python. And I do think that there are some, yeah. And I do think there are some problems with the multi-core scaling story with Python, but I think that Storm actually provides a gateway to solving a lot of them in a really simple way. And so this is actually a screenshot from 3 of my 7 or 8 Storm worker nodes running on my real-time data stream. And as you can see, every core in HTOP is fully lit up as it's churning through billions of tuples of data, and all of this is running in pure, sweet C Python, right? So I think you can get around it. I think that there's a great community emerging around Storm, and so let's walk through what Storm really is all about, like why it's such a great way to solve this problem, and also how we get Python to work on it. So actually, before I go into that, how many people here would say they already know how Storm works and have used it before? Okay, so a handful of you. So I'm going to give a brief overview of Storm, but I tried to make it really Python relevant. And the way I did that is I kind of cover Storm topology concepts using Python pseudocode. and actually using Python pseudocode that uses coroutines, which is kind of fun too. So that's how we'll actually cover how Storm works. Before I go into that, streamparse is really an integration library for Storm. So we're trying to make it like the Django of data processing pipelines. So you can just start a quick project in streamparse. It gives you a command line interface to work with your project. It gives you some basic scaffolding to start with. And then there are good management tools for working with a Storm project in pure Python. It's really good for analytics, logs, sensors, and other low latency use cases. So this is the rough agenda. I'm going to cover Storm topology concepts. I'm then going to go into Storm internals. I'm going to show how Python works with Storm. I'm going to give an overview of the streamparse API. And then I'm actually going to give you guys a preview of another library we're working on called PyKafka, which actually helps with another related technology. And like I said before, all these slides can be found on Twitter. So first, let's go into Storm topology concepts. Basically, Storm provides an abstraction for computing that can operate at cluster scale. And the abstraction is really simple. These are the four concepts you really need to know about. There are tuples, spouts, bolts, and a topology, which ties it all together. A wired topology looks something like this, where essentially there are components that are emitting raw data. That's the spout on the left-hand side. And there are components that are consuming that data, transforming it, possibly sending it to other components, and possibly having side effects like writing to databases and things like that. And that abstraction kind of covers pretty much every computing use case. Now, as I mentioned before, I'm going to use a little Python pseudocode here, so this isn't like production code you should be taking with you anywhere. It's just illustrating an idea. Although I did actually write a mock implementation of Storm using Python coroutines based on this code, so it's not totally crazy. So a tuple is kind of similar to the Python notion of a tuple. It's a data value. For example, you might have a tuple that represents a word, and so then it has a string value like dog in it. And the tuple spec for that would just be, hey, the first field is word. You could also have a tuple that represents a word count, and then maybe it has two fields, a dog and the number of times dog appeared in some corpus, which is 4 in this case. And that's pretty much the notion of a tuple. A spout, on the other hand, is a component that's going to emit tuples into your cluster. So this is like where your raw data comes from. And so the API for spouts is very simple. You implement something called nextTuple on some class, and it's called repeatedly. And when that function is called, you just get back data values, and they get emitted into your cluster. I wrote a little coroutine here, which basically, in a tight while loop that just spins, is grabbing tuples from this API. If a tuple exists, it's actually sending it downstream using generator.send method. And if it doesn't exist, then it just sleeps for 10 milliseconds and then re-retrieves a tuple again. And this is kind of modeling what Storm does when it works with your spout component. By the way, how many people here have written coroutines before? Oh, okay. So there's nothing really fancy about coroutines. They're nothing more than functions that are wrapped with a special decorator that primes them. And basically in coroutines, you can send values into a processing pipeline in the same way that generator functions let you return values out with the yield statement. So this is where the coroutine part gets kind of interesting, and then you could go look up coroutines later. In a bolt is basically a processing stage. So it gets tuples. Process gets called repeatedly with those tuples, and then it has to either acknowledge them, fail them, or emit new values into your topology. And the implementation for this could be shown with this coroutine here. And the interesting line here to look at is actually this yield that's in parentheses here. So this is yield being used as an expression. And basically what that means is this coroutine is going to wait for a value to get sent into it. When it receives that value, it's going to start processing it. So this is basically saying, wait until I get a new tuple. If I got a weird tuple that was none, then sleep for 10 milliseconds. If I didn't, call process repeatedly on the bolt. And then a topology is nothing more than a wired pipeline, right? A wired pipeline of these things. It's actually a directed acyclic graph describing processing stages. So if I were to do it with this little coroutine example, I would just have some classes like word spout, word count bolt, debug print bolt, and I'd wire them together. And then to start off the processing pipeline, I would just call Python next, and that would initiate a coroutine pipeline against all of that data. So that's kind of by analogy how Storm works. It lets you set up processing pipelines the same way that you might set them up using coroutines in Python, but it does this at a cluster scale. So the other thing that's kind of cool is Storm has a bunch of internals that make it work really well for processing large streams of data. One notion that's in Storm is called the Tuple Tree. And the Tuple Tree is that if you start with a sentence, for example, like the cow jumped over the moon, and you have a bolt that actually tokenizes that sentence and turns it into words and emits those, it'll keep track of the ancestry of that data. So it'll know that the cow that happened in processing stage 2 actually came from the sentence in processing stage 1. And then if a later stage does a word count, where it notices that cow only occurred once in your data, it'll also keep track of the fact that there was a tokenized word cow and a sentence that originated it. And that'll be important later when I describe how reliability works. Now, the other thing that Storm does is because you can partition your processing across your cluster, it has to give you a way to organize the data that flows between parts of your cluster, group data together on some key, and also parallelize different components in your cluster. And so in this kind of word count example again, I might have two components, a word spout and a word count bolt. And basically the input to the word spout is nothing. The output is the word count bolt. The tuple is the word, like dog, and the tuple that comes out of word count bolt is the count, which is dog and 4, let's say. The stream is word, and the stream on the word count bolt is word and count. The grouping is interesting. So basically what grouping lets me do is say, when you emit words, make sure the same words always go to the same bolt. So for example, if I group on word, it'll say, every time you get dog, make sure dog gets hashed to arrive at the same bolt later in the processing stage. And parallelism is also tunable per component. So in this example here, I might have parallelism of 2 for a word spout and parallelism of 8 for the word count bolt. And that means that it's using 8 Python processes on the right and 2 on the left. Now, Storm also has a high availability model, which is pretty great. What's going on there is that Storm actually is split up into several cluster components, which are called the Nimbus, the supervisor, the worker, and then there's a zookeeper cluster for coordinating cluster state. So when you actually deploy a Storm topology, you deploy it to this thing called the Nimbus. It sends your code out to the rest of the workers, and the worker processes are the ones that actually operate on your code. They also give you a little UI that lets you monitor what's happening. The workers all are able to stay online through high availability with Zookeeper, and that's kind of just handled for you automatically. Now, worker nodes are interesting because they basically are like processing slots in your cluster. So when you first deploy a Storm cluster, you're going to have a bunch of worker nodes, in this example 4, and there's going to be empty slots for each worker node. And when you deploy a topology, a certain topology may occupy certain slots across your cluster. And at some point, you might end up getting unlucky and your certain parts of your topology may occupy certain slots on one physical node. But it doesn't really matter because you can rebalance your Storm topology and basically get balanced computation across your cluster. So all this stuff I just described about Storm really briefly at a high level is also covered in a great book that just came out from Manning called Storm Applied. I wrote the foreword for this book, but the authors work at the ladders, and they've done a great job covering Storm internals. And some of these diagrams came from there too. Yeah, so Storm is sort of amazing as infrastructure. It'll actually guarantee processing of your data via tuple trees. It can do tunable parallelism per processing stage. It implements high availability. When you use it with Python, it allocates Python process slots on physical nodes for you. It can help you rebalance computation across your cluster, and it can handle network messaging automatically. And when you use it with Python, you're basically working around the GIL because you get process level parallelism without having to deal with async programming or multi-thread concurrency or anything like that. So let's get there. Let's actually get to this loaded up cluster that I showed before. So the way that Storm works with Python is through a protocol that's called the multi-lang protocol. The multi-lang protocol is basically a simple JSON protocol that works over shell-based components. You communicate over standard in and standard out. It's very clean and Unixy. For people who have used like Spark, for example, Spark tries to implement stuff like this with like weird hacks that go into the JVM. That's not what Storm chose to do. Instead, it's just a very clean, almost Unix-like system where you communicate JSON data coming out of your processes and you receive JSON data in. It's a little bit quirky, but it was easy enough for us to implement. Each component in a Python Storm topology is either a shell spout or a shell bolt. and Java implementations speak to Python via JSON. And the result of this is that there's one Python process per Storm task. So when you set your parallelism to 8, you actually get 8 Python processes on your machine. And there's kind of some data interchange that happens between Python and JVM. This is like a little illustration where when a Storm topology boots up, you have like a handshake that happens between your Python process and the JVM. And then data either stays within your Python process or moves to other nodes, depending on where that data needs to go. And there's also things like heartbeating mechanisms to keep tabs on whether your Python process is still alive or whether Storm needs to kill it and restart it and things like that. So Storm actually had a Python implementation bundled with it. It was called storm.py. The problem was it wasn't Pythonic at all. It was basically the single module written as a proof of concept. And you were supposed to copy paste that module into a jar that you would submit to your Storm cluster. Like they kind of assumed when you were using this that you were primarily a Java programmer who maybe had like JetBrains or something open, and you would copy storm.py into your Java project and thus be able to bridge over to CPython. So that was like the first thing that we thought we should fix. But in general, what we did with streamparse is we really turned Storm into infrastructure. The way I look at this is that a lot of people in this room probably use technologies like Cassandra and Elasticsearch with Python, and they do that comfortably, even though those technologies are written in Java. But probably most people don't use Storm because it feels too much like a Java tool. And what we're trying to do with streamparse is make it that Python is a first-class citizen in that community. And we also want to fix what we're calling Javanonics, which is the fact that unlike Pythonic code, a lot of code has like a Javanonic feel where like it really is built primarily by those idiomatic Java programmers. And certain things like using Maven for packaging seem very familiar in the Java community, but seem very foreign in the Python community. So now I'll dive into streamparse and give you an overview of that as well. So the initial release for streamparse was April 2014. We've done about a year of active development on it. It has about 600 stars on GitHub. It's got 90 plus mailing list members on Google Groups. We got 5 new committers through the initial release, and there's 3 Parsley engineers who are like maintaining it as part of their daily work. And we actually even got funding from DARPA to work on it and open source all of our work, which is pretty cool. And DARPA's actually been funding a lot of big data stuff lately. So streamparse, when you install it, what you get is this API, this command line interface, which is called sparse or sparse. And what happens is you pip install streamparse and you say sparse quick start, and kind of like a Django quick start, you get a Storm project ready to go in Python. It actually generates that word count example that I walked through earlier. The only dependency for streamparse is a tool called Lineagen or Line, which is basically a closure tool that knows how to resolve Java dependencies. So if you have that tool installed, streamparse connects to it and is able to like download Storm, download Zookeeper, download everything that it needs. If you then run sparse run out of the directory created by the quick start, you actually get a locally running Storm topology in memory that runs your code exactly the same way it would run in Storm remotely. So you just run sparse run, that's it. It takes about a second, and a word count topology is running locally on your machine, and it's already beating the GIL. It's already running multiple Python processes, coordinating with JSON and all that stuff. All the output comes out in your terminal, and I actually include a link in the slides here to a live demo I gave that was recorded on YouTube that kind of shows all of it working. I decided not to risk it here because of Wi-Fi issues and stuff, right? So submitting to a remote cluster is just as easy. You just type sparse submit. Magically, it does everything necessary to get your cluster up and running on a remote Storm cluster. It makes virtual envs on every machine in your cluster so that you have isolated dependencies there. It builds a jar out of your source code because that's what Storm requires, unfortunately. It opens an SSH reverse tunnel to your Nimbus node in your Storm cluster, and it talks to your Nimbus node in order to submit your jar there. And all of that basically gets your topology up and running in just a few seconds. So whether you've got a 5-node Storm cluster or a 500-node Storm cluster, you can get your production code going from local to remote in just a few seconds. I'm not going to go through this, but basically streamparse also improved a whole lot of other things related to storm.py in the IPC layer. Like we wrote tests, for example. We added logging support. We have it running in Travis CI. So, it's an actually maintained open source project instead of like a little hack. And by the way, it also supports Python 3.4 and PyPy, which is great. The bundled one doesn't support either of those, unfortunately. So now let's make a topology. So in order to let you make topologies and specify them, we take advantage of a DSL that's bundled with Storm. I'm not going to cover the details of this DSL, but the fraction of the code that you need to specify your topology is so small relative to the code that's written in Python that I don't think it's like worth covering it in too much detail. You can, for the most part, follow the examples in our read the docs documentation and always get there. Roughly what's going on here is that I'm creating something called a word spout. It has a certain Python class, which is implementing that streamparse spout interface, and I specify the stream, so the fact that this emits a tuple with a field called word. I then implement the spout, which is simple Python code like this. From streamparse import spout, create a class called words, which subclasses it, and then I only have to implement two methods, initialize and next tuple. And next tuple, like I mentioned before, is called repeatedly by the Storm cluster. So in this example, I'm just emitting one-word tuples from an endless generator that's cycling through these 4 words. By the way, what example of data processing wouldn't be complete without extensive focus on word count? I'm sorry for that, but it just actually does fit in slides nicely. So to specify the bolt that's going to count these words, you have to do a little bit more work. You have to say my input is word spout, which I spec'd out on the last slide, and I'm going to group on the word field. The class is, again, the class implemented with streamparse, and then I want to be able to emit the word and the count. And here I'm actually specifying the parallelism. I left it out. The default is just 1 when you don't specify it on the last slide. But here I specify parallelism of 2, which says it's going to use 2 Python processes for this. And again, the bolt fits on a slide as well. From streamparse import bolt, initialize method, then there's a process method. And in this case, the process method actually fetches the word out of the tuple. It increments a in-memory counter with collections.counter. And then it uses Storm logging to just log the current count of the word. And so this assumes that grouping is working because the in-memory counter for dog, let's say, is going to always receive every new dog tuple that comes into the topology. Another cool thing we implemented in streamparse is that we actually have a BatchingBolt for performance. So the BatchingBolt actually has a background thread that will batch your tuples together in whatever number of seconds you specify. And this can dramatically improve performance, especially for things like ETL use cases, where, for example, you're writing to Cassandra, Elasticsearch, or some other database in a batched way. It tends to be faster. streamparse also has a simple JSON configuration format that lets you specify multiple Storm environments. So that's like this is specifying here a Storm 0.8 environment. This is specifying a Vagrant environment. And you can switch between those using command line flags. So it just works. And streamparse has a whole lot of other commands too. Like you can list the topologies in your cluster, kill a running topology, tail log files on your remote servers. And we're adding more and more every day and actually very open to taking pull requests. So to close up, and then I'll open it up for questions, I also just wanted to mention that a lot of people use Kafka here together with Storm. Who here has heard of Kafka or uses it? Yeah, so Kafka traditionally hasn't had a great Python library, so we decided to take one we wrote internally about a year ago and port it to 0.8. And that's now live at PyKafka at the Parsley GitHub repository. It actually supports balanced consuming, which is a really important feature for getting it to work well with Storm at scale. So we're also looking for help with that module if you want to find me at the sprints. So I'm all done. I left a few minutes open for questions. I'm probably going to be sprinting on Monday and Tuesday on writing a Python DSL for Storm topologies, which I think will be a lot of fun. But I hope that this talk was helpful and hope to hear from you guys.
Okay, thanks a lot, Andrew. If anyone has any questions, please feel free to come up.
Hi, good talk, thanks.
Yeah, no problem.
Quick question, does this thing handle deploying Python dependencies with the bundle as it deploys to the Storm nodes?
Yeah, that's a good question. So you asked whether it handles deploying. Python dependencies in the jar that goes out to the Storm cluster. It doesn't do that.
Okay.
Instead, the approach we chose to take is we SSH into the cluster nodes, and we maintain virtual M's that correspond to the topology, and we update the dependencies live on those servers before actually submitting the topology jar.
So by the time the code reaches the server, it expects that those dependencies exist.
Exactly.
And it's started inside. Those processes are started inside of that virtual env.
Exactly.
Okay,
Yep.
cool. Thank you.
No problem.
Hi, Andrew. Thanks for the great talk.
problem.
Could you speak a little bit about the similarities and differences between this and something like Yelp's Pyleas library?
Yeah, so Yelp's Pyleas library actually came out around a few months after we released this, and we talked to the community there, and they have a lot of overlap actually. I have like a kind of couple slides in the appendix that cover that, which you can find online. But essentially, Pyleas also has a command line tool called Pyleas, which is handling the packaging part. It handles packaging a little bit differently than streamparse does. And the IPC layer is close to identical. So I'm actually going to probably propose to the Pyleas community that we try to share code on the IPC part. We actually registered a project called PyStorm, which we're planning to move the IPC part only into that. And then we could have competing CLIs with a unified IPC, ideally. So we're working on that in the community, but it's just parallel development efforts.
Cool, thanks.
No problem.
Awesome talk. So I've been experimenting with Storm, and this is like a Storm question, but
Sure.
how do you, so you mentioned that streamparse has logging, and a lot of times when your bolts die, it's kind of hard to figure out what's going on, get that introspection. So how does streamparse use the normal Python logging module, and how do you get that introspection instead of going through Storm UI or through the Zookeeper nodes?
That's a great question. Yeah. So this was something that we improved dramatically in the last 6 months in streamparse. So we actually make use of Python logging in the streamparse IPC module. And we set up a set of Python log files that are in the scratch area specified in your streamparse config. So on every node, there are Python log files there. And that's important because, first of all, we redirect standard out, or we redirect essentially sys.standard_out to Python logging because of the fact that the multi-lang protocol itself uses standard out. The other reason that's important is because we have an sparse tail command, which can go to your cluster and get the most recent logs. And that tail command knows how to find the Python log files on your Storm worker nodes. So if you just run sparse tail, you can tail the logs. And if your Storm worker crashes for some reason, you'll see the exception right there in the log files. Although a lot of people on my team are pretty interested in improving logging and debugging broadly, and that's one of our roadmap items for this year pretty much.
Thanks.
Yeah, no problem.
It's more of a Storm question, but
Sure.
last time I looked at this stuff, reliable processing was iffy. Basically, if something fails and gets rolled back, there's a good chance it's going to fail again and continue doing it till you die. And since you have a bit more layers there, the chances of this happening are higher. So is anything happening in this regard in Storm in general and in your project in particular?
Yeah, it's a great question. So reliable processing is just hard to get right, of course. I think the strategy in the community right now is that there's a really high usage of Kafka with Storm together. And at the very least, you can guarantee with Kafka that your raw data stream is maintained for some SLA so that you can replay those tuples at the source. And if you write your Spout the right way, implementing the reliability semantics that Storm provides, which are pretty easy to implement actually, then you can get some guarantees that you'll replay that data. You're right that there are many failure scenarios where replaying won't buy you anything, because if your code is broken, it's going to still be broken when you replay the data back into it after it crashes 100 times, right? But what I think Storm is trying to fix, and which we have found in production is true, is it's trying to help with the situation where ephemeral downtime of specific machines and specific services does not cause your entire data processing pipeline to fail and does not cause you to lose data. And I think that that's the primary use case that the reliability semantics in Storm tries to solve for you.
Okay, thanks everyone for your questions. One quick note, there are surveys up on the corner of the stage that the organizing committee is asking you to fill out about the closed captioning. If you could do that, we would really appreciate it. Have a great afternoon.
All right, thanks.